approach with the objective of identifying discoveries or results. Got it. So the objective here is to identify results from in a large-scale hypothesis testing setting that are worth moving on to the next stage of research to follow up in future research. And the ideas here, the method here is implemented in the FDR CI R package, which is available on CRAN. So to motivate the concept of permutation-based FDR, I'll describe this study that I was involved in. And this was an effort to profile samples from approximately 4,000 patients, tumor tissue samples from 4,000 patients with high-grade ovarian cancer. And to do this, we decided to use a nanostring platform to profile these samples, which were formalin-fixed, paraffin-embedded slides. And nanostring has a really nice, high-quality platform for extracting gene expression from this type of tissue. So we wanted to use the nanostring platform, but we could only have 500 genes on the array. So we needed to somehow select approximately 500 candidate genes to move forward with this study. Now, the main objective of this study was to identify gene expression associated with overall survival in these patients. And it's not that this was the first study ever to try to do that. There were other studies before that use other platforms and other tissue types and associated gene expression with overall survival. But typically these other studies were pretty small in the hundreds of patient samples range. And the thing is that they didn't agree. The sets of genes that identified as associated were very different from study to study. So we had access to data of a lot of these studies, so about 6 of them, which totaled about 1,500 samples. And the problem that we were faced with was how to use all these data and results to identify the 500 candidate genes. So the conventional way to do that would be to do a meta-analysis, or maybe take the data and do a stratified Cox regression analysis. But our concerns about those approaches was that, maybe because of this lack of agreement across studies, we thought there might be one or more of these studies that were problematic for whatever reason. The data could be, bad. And so we decided that an approach, a statistic that might capture what we wanted would be the median p-value for each gene across the studies. That way, it would capture a consistent effect across the studies, but allow for some studies to disagree from the others. But we also wanted to incorporate this idea that that the p-value isn't the only piece of important information, right? It needs to, the effect needs to be in agreement to some extent. So we decided that for the small p-values, if the effect was in a different sign between studies, then we would just set the p-value, the median p-value, to 1. So we were pretty happy with this statistic, but now, of course, it's not a proper p-value and we don't know what the distribution is. So the approach that I took here was to permute the data multiple times, compute FDR, and using the permutation-based approach, so we didn't need to know the actual distribution. So here are the results on the right. you can see the results from that analysis, which we just called the consistency analysis. So in the plot across the x-axis, we have candidate discovery thresholds. And on the y-axis are estimates of FDR and corresponding confidence interval, which is shown in that with that region, the gray region. And what you see, so then on the right here, the right plot is the stratified Cox regression. That's more of the conventional stratified Cox regression approach. And what you can see it for any given FDR value, like 0.05, the consistency approach actually gave us many more genes than the stratified approach. So this, it demonstrates that we can put together some statistic, not know the distribution, and still move forward, compute FDR using a permutation-based approach. And here we only use 100 permutations, so it's not like we need thousands and thousands of permutations to come up with these estimates. Okay, so first I'll just give a brief review of FDR approaches that led to the permutation-based approach that I'll describe. Then I'll introduce this idea of selection and adjustment of FDR confidence intervals, go through some simulations to evaluate that approach, and then describe an application to the Maverick colorectal cancer clinical trial. So FDR was first proposed by Benjamin and Hochberg in this paper, and it was really a groundbreaking idea at the time, because they proposed, rather than controlling the absolute rate of error, we would control the rate of the false discovery rate, which is the rate of false null hypotheses within our discoveries. So this is very different than controlling the family-wise error rate, because we're allowing for false discoveries within our discovery. And we're saying that some proportion of false discoveries are acceptable as long as that proportion is small relative to the proportion of true discoveries. So it's a much, much more powerful approach when multiple false null hypotheses are expected to be present in our data. So here we can describe the results of a study in terms of this table, where S is the number of total hypotheses that are called that are rejected. So those are the total number of discoveries. F is the number of null hypotheses that are true among our discoveries. So those are the false discoveries, and T are the true discoveries, the number of false null hypotheses that we rejected. So F and T sum to S, and what the classic FDR is, it's the expected value of this proportion F over S, given that S is greater than 0, because of course the proportion is not defined if S is 0. And so to get around this problem, we just define this value to be 0 if S is 0. That's how the original FDR is constructed. So I think probably most people know how FDR works. If the p-value is smaller than any p-value that's less than this value, I times alpha over m, where I is the indicator of the ranked p-values, then all p-values, all those p-values are considered discoveries at the alpha level. So a nice property of this FDR is that it does have weak control of family-wise error rate. That is, if the global null is true, then so there are no false null hypotheses, then the BH controlled FDR, the BH method controls the family-wide error rate. And you can kind of see that there is a link, an obvious link between the Bonferroni method and the BH FDR. If we have one discovery here, then it is the same as the Bonferroni method. We're just dividing alpha by m. So it's important to note, though, with the BH method that the way it's designed is alpha needs to be set before the data are analyzed. That's the properties are designed for setting alpha still and then estimating the error rate based on a priori chosen alpha threshold. So Story in the early 2000s turned things around, introduced the Q value, and introduced a way of estimating FDR that was slightly different than the BH approach and slightly more powerful, or under some conditions slightly more powerful, under other conditions substantially more powerful. But essentially they turned things around and said, let's just estimate FDR conditional on S being greater than 0. So conditional on having discoveries. And we can estimate FDR at each p-value, and we'll call that a Q value, because it's like the opposite of it's like flipping the idea of the p-value around, and that's why they called it the Q value. So a p-value can be thought of as the probability that a test is rejected given that the null is true, and the Q value can be thought of as the probability that the null is true given that the test is rejected. So they use this approximation that we can break the expectation up into two parts: the expected value of F divided by the expected value of S. It's approximately the same. They introduced this idea of pi naught, which is the proportion of true nulls, and a method of estimating that. And so they introduced this idea of estimation for FDR. That is, we can fix the rejection region and estimate FDR in a post hoc approach. And they also described a permutation-based approach, but here introducing the idea of estimation of a point estimator, so FDR is a parameter that we can estimate, naturally brings up the idea of the question of the variance of our estimator. Okay, so how good, it's not only the bias, so John Story's approach is less biased than the BH approach. It's still conservative, so that's nice, but what about the variance? So that wasn't really addressed, and that's where the approach that I introduced comes in. So I took a couple of key ideas, one in order to move this the estimation of FDR forward to incorporate a variance estimator. So one of the concepts was borrowed from Story and Tibshirani, and that's that we can break up the expectation of the proportion into two parts, a numerator part and a denominator part. And another key concept is that we can consider the S here to be a random variable that's a mixture of binomial variables where we have counts, a random variable of counts under the null and random mixture of binomial under the alternatives. So here we have this random variable. We can use the definitions of S and T, so we can estimate the expected value of S by S itself, and we can use the permutations to estimate the expected value of T and F, essentially. And going through this process, making another conservative assumption that M sub 1 minus T is 0. It's actually not an assumption, but a conservative approximation, and won't affect the estimate by that much. So this leads to an estimator that actually turns out to be an odds ratio, or you could consider it to be the odds of a positive test in the permuted data divided by the odds of a positive test in the observed data. So, and like an actual odds ratio, where we have this commonly used estimator, the Wolf estimator of variance, we can estimate the variance of the log FDR in the same way and use that to construct confidence intervals. So that's the initial version of the FDR approach with confidence intervals that I've developed. So now that's the background part, and I'll get into this idea of selection and adjustment of FDR confidence intervals. Does anyone have any questions up to this point? Okay, so how would we actually operationalize this? So with the BHFDR, it's very straightforward, right? We choose, or the way you're supposed to use BHFDR, we choose an alpha beforehand, usually at 0.05, and then we generate our data and we apply the BH approach, and that gives us the rejected the rejected tests. But now we have this idea of that we can actually set the rejection region in a post hoc approach. So that brings up the question of, well, how do we do that, and where do we set the rejection region? So anyway, so I'll just kind of go through the steps of how we would do this. We conduct the analysis in the observed data. We would conduct permutation analyses, each time permuting the data in such a way that our statistic is generated under the null distribution, assuming there's a way to do that in our analysis. Then we choose a discovery threshold or multiple discovery thresholds across a range of our statistic, right? Some range that we think our alternative nulls will, our statistics will fall across this range somewhere. So we choose these candidate thresholds, estimate FDR for each threshold in the confidence interval. So you can think back to that first slide I showed with that FDR plot and that discovery thresholds along the x-axis. And then we're free to choose, and from those candidate discovery thresholds, a final threshold or thresholds that we want to move forward with, depending on the characteristics of our study and the costs and benefits of future follow-up. So for instance, if the costs of following up on results of our current study, if the costs are cheap, and we can quickly follow up on many results, we may be willing to tolerate a fairly large FDR, and in the hopes that we'll get more true discoveries to follow up and eventually validate. And conversely, you know, if our costs of follow-up are high, we would want to make sure that the FDR is very low and we have high confidence that our discoveries are true. But if we take this approach, then we have many confidence intervals we're generating, and we will be probably cherry picking those low values of FDR. And so there's the danger that we might be biasing the FDR. So here it's a depiction of a confidence interval with the correct coverage. We know that interval is a random variable, so it's going to vary around the true parameter, and occasionally it will not include the true parameter, even for a confidence interval that has correct coverage. So there would be that danger of just picking the low one, even if our FDR would the true FDR would be very high. So this is the problem that we're trying to address. I mean, this is always a problem or an issue with multiple interval in a multiple interval setting, right? And there are many approaches that have been developed to deal with this issue in other contexts. Like, so one is the Bonferroni correction. So when estimating the interval, instead of using our initial alpha level, we adjust it. We divide the initial alpha level by the number of confidence intervals we're estimating, and then we have a Bonferroni adjusted interval. So Benjamini and Yucatelli in 2005 published this paper where they actually take a related approach to address this issue of multiple intervals. But they wanted to adjust the interval using the idea of false discovery rates rather than the family-wide error rates. And so in order to do that, they needed to develop this new way of evaluating coverage. So they define this new method of evaluating coverage, and they call that the false coverage statement rate, or FCR. And so here S is the number of selected confidence intervals. So this is a selection and adjustment approach. The intervals are selected and then they're adjusted. S is the number of selected intervals, so the number that get into our final set. F is the number of intervals that do not cover their parameters. And Q here is that proportion F divided by S, which is, of course, very reminiscent of the BH FDR. And we're trying to control this value of Q, the expected value of Q. So the selection part of the approach works essentially according to the BH method. So for each confidence interval, it's assumed that we have a corresponding p-value, and we apply the BH approach to select a set of tests that are FDR controlled. So now we have a set of selected intervals that are selected according to those p-values and BH FDR. That gives us this quantity R here. The Q here plays the role of alpha. So we have this R, and then you can see how this is essentially the same as a BH FDR approach. But then we can adjust we can develop a confidence interval and adjust it by this value. So in a Bonferroni corrected interval, we'd be dividing alpha by m. Here we're dividing it by q over m. So that's the difference. So you have an adjusted interval, and it still has this nice property that the Bonferroni adjusted interval would have. And that's that you can interpret if the confidence interval doesn't cover your null value, then it's going to be rejected by a standard BH FDR approach in this case. And if it does cover the null value, then it won't be selected in this case. So after reading this paper, I wanted to apply to the permutation-based FDR approach that I developed, and that, so it would solve this multiplicity problem. But that brings up another question, and that would be the p-value. So for the FDR approach that I've described, the permutation-based approach, we don't have p-values. It's just an FDR. It's just FDR and point estimate and a confidence interval. So the way that I chose to address that problem was to think about the null for FDR, and that seems to be the natural null to choose would be that the global null is true. So the global null is that FDR is actually equal to 1, right? So if there are any discoveries, all of those discoveries would be false. That would be the global null. Another way of saying that would be log of FDR is equal to 0. And the natural alternative would be that FDR is less than 1, or the log FDR is less than 0. So now we have null hypothesis, we have an alternative hypothesis. We know we have a variance estimator for the log of FDR, so we can compute a p-value. And this is the approach that I proposed in the paper that was recently published in Bioinformatics Advances. So essentially, the first 3 steps are using those p-values to select intervals. Okay, so the way it would work is the candidate intervals or candidate discovery thresholds are identified over a range of values that the statistic could take. And for those candidate thresholds, there are T of them. So here we have T of them. We generate T p-values. So now we have a p-value associated with each of those candidate thresholds. We have FDR estimates, we have FDR confidence intervals, and we can apply the Benjamini and Yekatili approach, select those intervals or select a subset of those intervals if they meet the BH FDR criteria, and then adjust them. So the nice, so then again, the nice property here is that we're controlling family-wise error rate in terms of those generated p-values associated with the confidence intervals. We're controlling family-wise error rate under the global null. So we control a family-wise error rate in that sense. Okay, so now I'll go through some simulations where the approach was evaluated. So there are other possible ways we could select an interval, right? Just heuristic approaches to selecting an interval from our set of candidate thresholds and the intervals that we compute for each threshold. So one approach would be to select the interval if the upper confidence bound is less than 1. So that's essentially the approach that I have been taking, and looking at the confidence interval, saying is if the upper bound is less than 1, or at least somewhat less than 1, then it's probably it's probably the FDR is probably low enough to be meaningful, for the point estimate to be meaningful, and the confidence bound to be more meaningful. But another method could be, if the point estimate is below 0.2 or below some value, then maybe we're interested in that interval. And those two are the approaches that we can contrast to the one I just described, which is basically using the BY method and these p-values that I just described associated with the candidate thresholds. So the simulation parameters are sample size of 200, 100 predictors, 20 outcomes, and the analysis here is looking for association, so correlating outcomes with predictors. Each outcome is dependent on a block of correlated predictors. So the 100 predictors are actually blocks of correlated blocks, 20 blocks of 5 correlated predictors. And so there are 2,000 tests total, because we're looking at all the correlations between the predictors and the outcomes. So we know what the truth is. We can calculate the true FDR, and we can take a permutation-based approach to recompute the data, generate multiple permutations. The thresholds in the simulation, I set a series of thresholds from negative log 10 of p-value equal to 2, equally spaced, up to 6. Knowing that if there, for these data, if there's an association, it'll most likely fall in that range, the p-value. So there were 5 scenarios simulated. A through E are the 5 scenarios. E is a special scenario because it's simulated under the global null of no association between any of the predictors and any of the outcomes. A through D varied in terms of the number of false null hypotheses and the strength of effects for those hypotheses. And okay, so here you have the coverage in the lower left table. There's coverage under these different scenarios for the 3 selection approaches. And coverage here is defined as 1 minus FCR. Okay, so we're using FCR to evaluate coverage. It still should be 0.95, for perfect coverage would be 0.95, using an alpha level or an FDR target level of 0.05. And what you see here is for the scenarios A through D, which all have false null hypotheses, coverage is conservative overall and pretty good. Maybe a little conservative for some, but basically good and certainly conservative. For the global null scenario though, E, there's an obvious problem with the upper confidence bound approach. And there's also a problem with the selecting the interval if the point estimate is 0.2 or below. That also generates a problem. So coverage is low, anti-conservative. But we see that the BY approach, the proposed approach, does a good job of controlling coverage under the global null. If we look at the figure here, it shows conservative coverage under the scenarios A through D, and it shows conditional coverage. Conditional coverage is the coverage only among the selected intervals. So we can see that there is a substantial problem with the even among those scenarios with true null with false null hypotheses, there's a substantial problem with the 0.2 approach. So but the proposed approach has conservative but decent coverage across this whole range. Okay, so the application to the Maverick clinical trial, there's 329 patients with metastatic colorectal cancer. They were treated there were 2 treatment arms, FOLFIRI plus bevacizumab and FOLFOX6 plus bevacizumab. The outcome that I'll show here is progression-free survival. All these patients were profiled with the OncoArray 500K SNP panel. Using these data, the GWAS data, we generated genetic imputed gene expression using models from the predictdb.org. And the final data set here was included 5,520 predicted gene expression features. The objective was to identify genes that were both predictive or that were either predictive or prognostic. So predictive implies that there's an interaction between treatment and the gene expression feature. So, and the analysis was was repeated for each gene individually. We applied a Cox model, adjusted for age, sex, the performance score, ECOG, number of metastases, KRAS, mutation status, and it was stratified by geographic region and excision repair cross-complementary group 1, ERCC1 expression levels, high or low. 100 permutations were conducted, and the genetic matrix, the TWAS data were randomly permuted for each permutation. So 100 sets of results were generated according to this analysis with likelihood ratio tests for the delta parameter and omega. A series of candidate thresholds were chosen as in the simulations, and FDR, the confidence intervals and adjusted confidence intervals computed for each one. So here in this FDR figure here, you can see the results. The numbers in the field are the selected number of discoveries at each candidate threshold. Here you have the 2 shades of gray, which represents the unadjusted confidence intervals and the adjusted intervals. So you can see that the adjustment process causes the intervals to become larger, but just by a little bit. In this situation, it doesn't actually expand the intervals by much. 4 genes were identified, so a reasonable discovery threshold, I decided, would be in this neighborhood, yielding about 4 genes with an FDR of about 0.24. So estimated by the MV approach, the FDR is 0.24. Estimated by the BH approach, it's 0.21. So if we look at the Q values here for the BH approach, and the MV Millstein-Wolfson approach, you can see that the estimated FDR is really actually very similar. And I think that indicates two things. One, that the parametric assumptions of the Cox models held well. And so the BH FDR is in agreement with the MV FDR, which is a permutation-based approach, and the permutation-based approach captured the true null distribution pretty well. Now, here are the unadjusted intervals, and on the last column are the adjusted intervals, and you can see again that the difference is not great in this situation. So there's minimal impact to the interval width in some situations, depending on where the adjustment intervals are where the candidate thresholds are selected. But also there's, of course, high dependency between these thresholds. And that's another reason, I think, why the adjustment has pretty minimal impact. If we look at Kaplan-Meier curves for these results, we can see why these genes were identified as an interaction between treatment and the effective expression on progression-free survival. So for instance, if we look at the WD sub1 gene, dividing it into 3 groups, low, medium, and high, dividing the predicted genetic imputed gene expression into 3 groups, we can see that low predicted expression is the worst, high is the best in patients treated with FOLFIRI-Bev combination, but the reverse is true in patients treated with the FOLFOX6-Bev. So low expression, predicted expression is good here, and high is bad. And a similar thing is going on with the CAVN3 gene, how the curves flip from one treatment to the other. And again, you can see it with the other 2 genes. So all identified as having that interaction or predictive effect.
So they all kind of have crossing interactions, right?
Well, that's the interaction, is that the relationship between the curves flips across treatments.
And I mean, does it make biological sense? You've been able to make sense of that in any way?
You could almost always spin a yarn, right? Like come up with a justification. But we have looked at some of these genes in other data sets, and although some effects have been apparent, it's not all that consistent. So it's just not obvious what's going on. Different populations, different treatments a little bit, different focus of studies, or we've looked in TCGA, but TCGA is a very heterogeneous group of patients in cancers, and we don't have treatment information. So it's sometimes really hard to follow these up. But that's basically what I wanted to present today. So thanks a lot. And I'd like to thank the lab of Hans Joseph Lenz, who helped with the data analysis, interpretation, and thanks.
Any questions in the room or online? Okay, well, thank you, Josh. That was excellent.
All right.
Thank you very much.